So we continue with the applications of various efficiency measures. Well, we learn price of anarchy and price of stability, but it can be done with respect to various solution concepts. So most common is of course the Nash equilibrium and mixed Nash equilibrium, and with respect to various definitions of social welfare. So most common is of course the total utility. So we continue with the applications. And as I probably have already mentioned, the applications are these are extremely important. These are simple, but in general, applications like that, only others, are right now an active area, active study areas. So basically now we are touching, I can say, this very hot and flowing and living area. So the application is called scheduling games, and that is a model of scheduling competing tasks on identical machines. So the definition, well, let's consider the following game, which is called simple scheduling game, which, as all these lecture pretty much, is taken from the book Algorithmic Game Theory, from excuse me, that's taken from section from chapter 17, and the game consists of M. Here we have M instead of N jobs and machines. And the jobs are the players, so they decide to which machines to go. And we have M instead of N because the number of jobs and the number of machines need to be equal. So we can say that we have N jobs and M machines, but we require here M is equal to N. So anyway, we have M jobs and machines, and a player, as I said, the jobs are the players, I chooses the machine. So the set of strategies of player I is a set of machines. And the utility of a player given the profile, so Mi is the machine that is chosen by a player, is by player I. The utility of player I is minus the number of players that choose the same machine. So the more congestion there is on the machine where I go, the more I suffer. It's clear. We can even say that the cost is the number of players or that choose the same machine, or we say here that the utility is minus the number of players who choose the same machine. And I say who, of course, the players here are it, because they represent jobs. Though, of course, the person who owns the job probably can decide. Anyway, so the players, the jobs are the jobs, social strategies are the machines, and these are the utilities. And now here we immediately see that the Nash equilibria of this game, they are the set, excuse me, all the profiles, also all the choice profiles of machines, the strategy profiles are here, choice profiles, all set M1 till MM, such that any couple, any pair of different players go to different machines. So there are basically M factorial different settings, different orderings, who goes where, such that every player goes to a different machines. All those divisions where each player goes to another machine, every such division is Nash equilibrium. Why? Because if you have such a division, nobody can improve her utility, of course, because everyone is alone. So everyone has the minimum possible utility, or no one is on the same machine. Now, on the other hand, if that does not hold, though if there is a couple of players who are on the same machine, it means that there is at least one empty machine, because the number of players and the number of machines are the same. So any player of those who are together can improve her utility by moving, by unilaterally deviating and going to an empty machine. So if this condition that any two players go to different machines does not hold, that's not a Nash equilibrium. So the second Nash equilibrium, as we have now argued, is a set of all the permutations, basically, or in other words, of all the choice profiles when no two machines, no two players go to the same machine. So when each player goes to some machine where that player is the only task, the only job. And the first simple statement, well, all the same statements here are nice and short. They're not necessarily simple, but they're nice and short, so I think it should be really easy and nice and pleasant to follow. So the first thing that we define is that the social welfare here is not the sum of the utilities, but it's the maximum utility. Why? I wanted to say that it's the minimum utility because, yeah, I wanted to say the utilities are the costs. 1 second, please. Okay, so I thought I would present the game in the language of utilities, simply taking the utility to be minus what we want to minimize, minus the number of jobs who work on the same machine. But I think that it will be easier to talk in the language of cost, as it often is when we minimize something. So I'm going to talk in the language of cost now. And so we define the cost of player I given profile M1 till Mn as the number of players that choose the same machine as player I. And now the social welfare, or the social cost, is not the total cost, but we here use the idea which is often used in the case of scheduling, and that is the idea that the last person, or the person who suffers most, has to be cared for. So we want the maximum cost to be minimized. So the social cost, which we care about, is the maximum cost. And we prove that the set of all the profiles that minimize the social cost, so the set of all the socially optimum profiles, is exactly the set of Nash equilibria. So the stability and the social cost exactly coincide here. Okay, that's an important and nice lemma. And the proof goes in two directions because it's inequality of sets. So if a profile is a Nash equilibrium, then we need to prove that it's a profile which minimizes the social cost. And indeed, the social cost cannot be improved since in Nash equilibrium as we said, every player is alone, so every player's cost is minimized. Yeah, I say every utility. I wanted to say every place. Cost is minimized. And therefore, we've just shown that if you have an Nash equilibrium profile, then it also minimizes the cost, so it also belongs to the set of the minimizers of the social cost. Conversely, if you have something which is not in a Nash equilibrium, we're now going to show that it does not minimize the social cost, and that because being not in Nash equilibrium means that there are some players, I and J, who are different, but such that the machines they choose are the same. Now, it means that the social cost, which I remind you is the maximum cost, is at least 1. Because I and J both, excuse me, is strictly larger than 1. Because I and J both are not alone, so they have to incur costs which is at least 2. Now, on the other hand, every profile which is in Nash equilibrium, its social cost, so the maximum of the cost, is 1. So the social cost of the profile we started with can be made, it's not the smallest possible profile. So by starting with a profile which is not in Nash equilibrium, we show that it is not a profile in argmin of social cost. And thereby we have proven the second direction. So if something is in Nash equilibrium, then it minimizes the social cost. If something is not in Nash equilibrium, then it does not minimize the social cost. And therefore the set of argmin of the minimizer of social cost and of Nash equilibrium pure. We are going now to talk about mix, but that's for pure till now. These sets are equal. In particular, all the Nash equilibria are optimum, so price of stability and anarchy are 1. And again, here I have a typo, my apologies. I've checked the slider somehow. I've missed several funny typos. So the price of anarchy equal to price of stability is equal to 1. And that minimum social cost, which is achieved in any equilibrium, is 1. Now let us talk about mixed. So the set of mixed equilibria includes the set of pure equilibria, and therefore, the price of anarchy bound can increase. And indeed it does in this case. So first we prove that the concrete profile, that each player chooses the uniform distribution of all the machines. So randomly chooses with equal probability one of the machines to run on. Then this profile is a mixed Nash equilibrium. It's a mixed Nash equilibrium. You don't say these are all the Nash equilibria, all the mixed Nash equilibria, but that profile is a mixed Nash equilibrium. So, as we already see, here the set of mixed Nash equilibria strictly includes the set of Nash equilibria. It does not yet mean that the price of anarchy will increase, but we are going to show that it's going to increase. So first we are going to prove that this profile is a mixed Nash equilibria. And the intuition is that that every player has the following picture. All the others play symmetrically. So all the machines are equally loaded in expectation. And therefore, given a certain player, and given any player, any strategy is the best response. Therefore, therefore, for that player also being uniform is the best response. Okay, formally, so what I just said is pretty much the proof, but formally, let xij be the following indicator variable. It indicates that player I selects machine j. So if the event mi is equal to j takes place, the random variable receives the value of 1, and otherwise means that mi is not equal to j. That random variable is 0. So that implies that for any player selecting the pure strategy, a concrete j, the cost the player will incur is the number of players who have the same, who choose the same machine. And that is 1, because that player itself is on that machine, plus, we are talking about expectation, the number of other players who choose the same machine, so the i's who are not k. We look at the xij, who are those from not k who go to machine j, and therefore the expected cost, so that's a concrete realization of a concrete cost, even a concrete realization of this randomization. Now the expected cost is 1 plus the expected cost of the sum, which is, by the linearity of expectation, the sum of the expectations. And that means that each of the expectation is the expectation that player I chooses machine j, and in the uniform case it's 1 over m, and we sum over m minus 1 such, so it's 1 plus m minus 1 times 1 over m, and that's equal to 2 minus 1 over m. And that is the same for any player n in n, for any player k in n. So any pure strategy is the best response, because the utilities does not depend, as I said before, there is symmetry. So utility does not depend on which machine the player chooses on k, and therefore any pure strategy is the best response. Now, by the definition of mixing, therefore any mixed strategy is the best response. So for any player, in particular, the uniform strategy is the best response to the uniform strategy of others. Please pay attention that for a given player, the best response can be any mixed strategy. But in order for that to take place, the others need to play uniform. So the others play such that every single player will have this ability to mix. And so we have proven that this strategy profile is a mixed Nash equilibrium. So it's at least one of the possible mixed Nash equilibria. And if you look at the expected value for any j, the expected value of those who play j in these uniform cases is of course 1, and then the maximum is also 1. But the maximum of the cost is not the expected value of the maximum, but it's the expected value, it's not the maximum of the expected values, but since the cost itself is maximum, it's the expected value of maximum, and that's not 1. That can be shown, we don't do it here, but it can be shown to be set of, so order of log m over log n. So it actually is something which goes to infinity as the number of machines or jobs goes to infinity, and very low, very slow indeed, sublinearly, but it does go to infinity. It goes to infinity even slower than log, but it does go into infinity. So while the price of anarchy and stability, of course, was 1, the price of anarchy of the mixed game, of the mixed extension, is at least order of log m over log m. Actually, that can be proven to be exactly this order, but again, we don't do it. Okay. So we have seen that the price of anarchy is 1 of the pure game, and then if you look at the mixed extension, the price of anarchy indeed increases. So that's in particular an example of the increase of price of anarchy as a function of the solution concept. Because we can look at Nash equilibrium not only as a Nash equilibrium of the mixed extension, but as another solution concept. Now, so that's an example of the dependency of the efficiency of the dependency of efficiency on the solution concept. Now let us look at another interesting case, and that's about the dependency of the efficiency on the social cost. So now let us take the social cost which you usually take, which is just the sum, so that's the utilitarian social cost. Not the maximum, but the sum of the cost. So we just want to minimize the sum of the cost. So first we show that again the arg mean of the social cost, this new social cost, is exactly the Nash equilibrium. So first of all, the set of Nash equilibria are all the sextant, all the players choose different machines, actually, because the definition of Nash equilibria does not depend on the social cost, so that statement has to remain true. But moreover, the statement that the set of profiles that minimize the social cost is exactly the set of Nash equilibria, that statement which does depend on the social cost we choose, that statement also keeps being true, as we now prove. So the proof is quite simple. So for any Nash equilibrium, the social cost cannot be improved because every cost is minimized, and therefore the sum is minimized. So the set of Nash equilibria is a subset of the profiles which are minimized of the social cost. Conversely, if something is not a Nash equilibrium, it means that there are some players I and j, different players, such that they choose the same machine. And then the social cost of this profile is at least, so the machines which are not I and j, there are m minus 1 of them, they incur cost of 1 at least, because every machine is at least with itself, any job is at least with itself at the machine. And machines I and j, those two machines incur cost of at least 2. Because each one of them is at least with the other, with itself and the other machine, the other job at the same machine. So the social cost incurred by this profile is strictly larger than m, because it's m minus 2 plus 4. So it's m plus 2. It's strictly larger than m. On the other hand, we know that any Nash equilibrium incurs the social cost of m. So the social cost of this profile, which we took, S1 till Sm, is not minimum. So we have proven the lemma. So if something is a Nash equilibrium, then the social cost of that profile is minimum, and if something is not a Nash equilibrium, we have shown that the social cost is strictly larger than the minimum possible. And we've proven the lemma, and that means that price of stability, and of course price of price of anarchy and price of stability above 1, and I again have to fix that typo. But the minimum cost here is not the maximum but the sum of the cost, and here it's m. Now, does the price of anarchy grows here too when we go to mixed? It does, but it grows differently than it did for the egalitarian cost. And let us exactly prove how it grows. I think it's a nice proof. So it's like a very simple but useful technique. So first, let us take a uniform distribution. We have already seen that it's a mixed Nash equilibrium, and that does not depend on the definition of social cost. So that is a mixed Nash equilibrium that we know. Now, using that and some other things, we are now going to prove that the price of anarchy, given the utilitarian cost and the mixed Nash equilibrium, is exactly 2 minus 1 over m. And the proof is as follows. So we first prove the price of anarchy is at least, and then that it's at most. So we prove it by first looking at the minimum difference between the value, the cost of an equilibrium and the optimum cost. So the expected cost is the expectation of the sum of the costs. From linearity, it's the sum of the expectations. And okay, I'm talking about this concrete price of concrete mixed Nash equilibrium when everyone plays the uniform distribution. So the sum of the expectations that of the cost, then everyone plays the uniform distribution. Now we already calculated before what will be the expected cost in that case, and that's 2 minus 1 over m, right? We can go back and see the expected cost in this case is 2 minus 1 over m. So here. and there are m players, so it's m times 2 minus 1 of m, it's 2m minus 1. So that's something which can be this cost. This cost can happen in a mixed Nash equilibrium. Now, let us bound from above what is the maximum cost that can be in a mixed Nash equilibrium. So let Q1 to Qm be any mixed Nash equilibrium. Not necessarily this uniform one, but any. And consider any player K. Now, the expected cost of player K for choosing this, let's start with pure machine M, is 1, so itself, plus all those others who are on the same machine. Now, since that's a mixed Nash equilibrium, we know that since there is now, okay, not so we know that there is a machine such that the total expectation of players there is at most m minus 1 over m, because the total expectation of other players is at most m minus 1, and there is a machine such that there it's at most m minus 1 over m. Now, since that is a mixed Nash equilibrium, then the player optimizes, so the player pays at most 1 plus this m minus 1 over m, which is 2 minus 1 over m. And the expected social cost is therefore the total cost of all such k's, because what we have done is true for any player k. And we simply multiply this 2 minus 1 over m by the number of players m, and that's 2m minus 1. So we've proved now that the maximum cost in any mixed Nash equilibrium is 2m minus 1. By the way, recall that a pure equilibrium, which is also mixed, incurs only the cost of m, but the maximum cost is 2m minus 1. And there, at most 2 minus 1. And there exists an equilibrium which incurs exactly this cost, 2 minus 1. Namely, this profile P1 till Pm, which is the uniform distribution. And the ratio of this one, of this worse equilibrium, which we now have proven to be worse, to the optimum social welfare, the less cost M, is 2 minus 1 divided by M, which is 2 minus 1 of M, and that's the price of anarchy. So here the price of anarchy has grown from 1 to 2 minus 1 of M, which for large M is close to 2. But while for the previous, for the egalitarian utility function, the price of anarchy was set of log M over log M. So there, for large M, it would be going to infinity. Very slowly, but it would be going to infinity. So both the solution concept and the cost, or social cost function, we look at matter. And of course, we choose the one which is appropriate to the problem at hand. Now let us look at another problem, which is resource allocation game.